The electrostatic force that stationary charged objects exert on each other depends on the amount of charge on the objects and the distance between them. Experiments reveal that the greater the charge and the closer together they are, the greater the force. To set the stage for explaining these features in more detail, let's look at the interaction between two charged bodies. These objects are so small compared to the distance r between them that they can be regarded as mathematical points. The point charges have magnitudes q1 and q2. If the charges have unlike signs, each object is attracted to the other by a force that is directed along the line between them. Plus F is the electric force exerted on object 1 by object 2, and minus F is the electric force exerted on object 2 by object 1. If the charges have the same sign, both positive or both negative, each object is repelled from the other. The repulsive forces, like the attractive forces, act along the line between the charges. Whether attractive or repulsive, the two forces are equal in magnitude but opposite in direction. These forces always exist as a pair, each one acting on a different object in accord with Newton's action-reaction law. The plus and minus signs associated with the forces in these diagrams are only to indicate that the two forces in the force pair are oppositely directed. They do not have to point along a specific axis, but rather on the line that joins the charges. In any given problem, the two charges could be located anywhere and oriented in any direction. In every case, the forces are always directed along the line that connects them and will be treated as any other force you have encountered, meaning you may have to find the vector components, magnitudes, directions, etc., and, in the case of multiple electrostatic forces acting on the same charge, use vector addition to find a resultant force. The French physicist Charles-Augustin de Coulomb carried out a number of experiments to determine how the electric force that one point charge applies to another depends on the amount of each charge and the separation between them. His result, now known as Coulomb's law, is stated as follows. The magnitude F of the electrostatic force exerted by one point charge Q1 on another point charge Q2 is directly proportional to the magnitudes Q1 and Q2 of the charges and inversely proportional to the square of the distance r between them, or F equals K Q1 Q2 divided by r squared, where the constant K equals 1 over 4 pi epsilon naught, which equals 8.99 times 10 to the 9th newtons times meter squared divided by Coulomb squared, and epsilon naught is a constant called the permittivity of free space. The nature of Coulomb's law has a lot in common with the law of gravitation. If you recall, the gravitational force between two masses, m1 and m2, separated by a distance r, is given by F equals g m1 m2 divided by r squared, where g is a constant. It is an inverse square law and has the same form as Coulomb's law. The gravitational force, however, is only attractive. Coulomb's law, as we have already seen, can be either attractive or repulsive. The electrostatic force, relatively speaking, is also a much stronger force than the gravitational force. Consider two charges with the given values, separated by 1 meter. What is the force on Q2 due to Q1? This is a straightforward application of Coulomb's law. We find F21 equals K times Q1 Q2 divided by r squared, which equals 8.99 times 10 to the 9 newtons times meter squared divided by Coulomb squared times 1 times 10 to the negative 4 coulombs times 2.0 times 10 to the minus 3 coulombs divided by 1.0 meters squared. Canceling the units coulombs and meters, we have F21 equals 1.8 times 10 to the third newtons. This corresponds to a force of over 400 pounds. Now, let's examine the case of three charges. We won't make any calculations, but we'll specify the signs of the charges. Q1 is positive, and the other two are negative. We want to find the force on Q1 due to the other two. Just to note, we could ask three possible questions with this charge configuration. What's the net force on Q1 due to the other two? What's the net force on Q2 due to the other two? And what's the net force on Q3 due to the other two? For this example, we'll look at the net force on Q1. We can start by drawing in the forces without knowing the magnitudes. This will set up the basic geometry of the problem. Since Q1 is positive and the other two are negative, and we know the forces must point along the lines joining the charges, we have one force pointing along R13 from Q1 to Q3, and the other pointing along R12 from Q1 to Q2. The magnitudes of these forces are given by Coulomb's law. F13 equals K Q1 Q3 divided by R13 squared, and F12 equals K Q1 Q2 divided by R12 squared. Once you have the direction and magnitude information, the problem reduces to a free body diagram-like problem and can be treated like all other multi-force problems you have encountered. In our case, with just two forces to consider, we can use our favorite vector addition procedure to find the net force. Here we show the parallelogram method to demonstrate visually. Of course, you will be asked to find magnitudes, components, directions, etc. in various problems. In summary, Coulomb's law is given by F equals K Q1 Q2 divided by R squared, where K equals 1 over 4 pi epsilon 0, which equals 8.99 times 10 to the 9th newtons times meter squared divided by Coulomb squared. The direction is given by the rule, unlike charges attract and like charges repel. Finally, when finding the net force on one charge to multiple other charges, compute the force from each charge independently and then add them all together using vector addition.